The attitude control for aerial vehicles is crucial for their stability and performance. Imagine a multi-rotor aerial vehicle that is solely controlled in its translation. It swings while tracking a desired trajectory but never loses stability, much like a flying pendulum. We designed such a miniature aerial vehicle simply by combining a lighter-than-air balloon and a special quadrotor. We named it SBlimp.
Hello everyone, my name is Jiawei. Welcome to my presentation of our paper, SBlimp, Design, Model, and Translational Motion Control for Swing-Blimp.
The major advantages of an SBlimp are its energy efficiency and the ability to translate in any direction, which make them more suitable for certain tasks than other aerial vehicles such as long-distance drone delivery and aerial construction. Furthermore, its simplistic design and natural stability allow us to design a translational motion control that drives the blimp in any arbitrary direction without worrying about the rotational swinging arrow. One of the most important principles of the SBlimp design is its simplicity. 4 3D printed motor ports serve as the connectors between a quadrotor and the lighter-than-air balloon, creating a rigid connection between these two major components. The simplicity does not infer triviality of our design. We highlight the unique actuation component of the SBlimp, which is a special quadrotor that has an unconventional rotor configuration. Different from a normal quadrotor, the one on an SBlimp has all its propellers not perpendicular to the quadrotor base, which took the inspiration from the T module of our previous work on H-mod quads. In such a rotor arrangement, the blimp can generate force vectors spanning the entire Euclidean space. We take a 2D simplification of the SBlimp for the dynamic analysis because of its symmetry and invariant coupling relations between the translation and rotation. We use Newton-Euler equations to describe the dynamics of the blimp. Note that we model the air friction as a damping term proportional to the blimp velocity under low speed for both translation and rotation. The motor dynamic matrices AF and A tau describe how the input U, which is a vector of the rotor forces F1 and F2, are mapped to the force and torque in the blimp body frame B. The rotation matrix R transforms the force from the body frame into the world frame. These two matrices depend on factors such as rotor position AX, AZ, and rotor angle etas. The torque generated by the buoyancy tau b due to the balloon force Fb is the key to the swinging behavior of the blimp, which comes from the misalignment of the center of mass and center of lift. Such a misalignment creates a torque counteracting the tilting in pitch, which results in a swinging behavior like that of a pendulum. When the rotors are actuating, the blimp swings while translating. Considering the damping terms in the Euler's equation due to the air friction, such a swinging behavior vanishes eventually, rendering the SBlimp's natural stability in pitch. Based on this natural stability, we apply a velocity controller only for translation. The velocity arrow is used to determine the desired force in the body frame that drives the blimp to follow the desired trajectory. Remark that since the rotors are not collinear when eta angles are not 0 or 90 degrees, AF matrix is full rank, meaning that we are able to inverse the AF matrix to achieve static feedback linearization to generate the desired force in the blimp frame to compensate for the velocity arrow. Here, KV is the feedback gain matrix. Such a translational controller, although not concerning the pitch stabilization, drives the pitch angle to 0 because of the SBlimp's natural stability. We show on the paper both in math and in numerical simulation that the pitch is asymptotically stable. We developed a 2D simulator in Python to show how some factors can affect the tracking error experienced by the SBlimp. We built a prototype using a Crazyflie micro quadrotor and a 36-inch helium balloon. The experiment shows that the blimp is able to hover precisely, stay airborne for a very long duration, follow a trajectory until hitting the speed limit, etc. As an actively progressing project, we recently built a new SBlimp without using the Crazyflie platform. The total cost of the blimp is therefore reduced to less than $35. Thank you for attending our presentation.